In this video we're going to look at the stability of an op-amp with negative feedback. So we've drawn out the circuit here for our op-amp. So we have our input here, Vin, and we have our differential amplifier here, which takes this signal here and then takes away this signal and multiplies the difference. And we're going to have some forward transfer function G of S, and we're going to have some feedback, and that's given by another transfer function H of S, and this is the output. So we'll call this little point here VE. So it means that this point here, this end here, is going to be VE times our G of S. So we can analyse this little circuit by noting that the V out is equal to VE G of S, but we know that that value of VE is equal to the V in minus the feedback here, which is VO H of S. So then we can replace the VE here with what we have down here. So we're left with VO equals the G of S times the V in minus VO H of S. We can multiply out the brackets, in which case we get this here. We can then, after multiplied out the brackets, we can take over the like terms, and we can gather like terms and have a coefficient of V naught. So we take out the V naught here, and that leaves us with 1 plus G of S H of S equals G of S times V in. So it means we can write the V out upon V in is equal to our G of S upon 1 plus G of S times H of S. So it means that we can rewrite that there if we divide through it out by G of S by this here. Now we know that, as we've seen before, that the gain of an amplifier ideally should be tending towards infinity, so that value G of S should, the open loop gain should be infinity, so that term there would tend towards 0. So it means that the transfer function there is really only going to be determined by the value of the feedback transfer function H of S and not the transfer function of the op-amp. Okay, so we're only interested in the feedback network, because that's the feedback network determines the transfer function of the circuit with the op-amp in it. Now the advantages of using this system is that we've got a noise reduction, there's less frequency distortion, it's a stable voltage gain, less amplitude and phase distortion, it's a controlled input and output impedance, and we can define the linear operation of the circuit, meaning we can go and build useful circuits, for example filters. Okay, so we've kind of seen this before anyway. We derived this same sort of equation, but it was in terms of a complex frequency. Okay, so let's move on, and we can see that what we're interested in is looking at the stability of a system with negative feedback. Now let's consider we put some input signal in, so there's a sine wave going into this op-amp here, and this is going to give us a gain, so there's a gain at the output here. It's going to be Vin minus Va times some gain factor, and we're going to take some part of it and we're going to feed it back to the input of the op-amp using negative feedback. But let's say, for instance, the phase gets shifted by 180 degrees round the loop. Okay, so it means that what's coming back up in here is the same as this signal here, but it's phase shifted by 180 degrees. Okay, so it means that whenever we add these two signals together, we're going to get this signal minus this signal here. Okay, so it's that height there minus the negative value, so it would be in fact that height plus that height which is going to give us an even bigger signal. So it means that if we feed that back again at this frequency here, we're going to get an even bigger signal. And so if we feed it back and the feedback loop continues, what's going to happen is we're going to get a huge signal coming out here at this frequency. So it means that at this frequency the op-amp doesn't work, okay? Because what's happened now is instead of having a circuit that's got negative feedback, the circuit has now got positive feedback, okay? So have a wee look and you can see there I've got it drawn there as well. So this is our input and that's our feedback there. So when this value here minus that value there is going to equal the bigger value there, because remember it's like saying 3 minus 3, which is 3 plus 3, which is 6, which is a positive value. Okay, so that is a problem, and we're going to look at that in the next video when we look at Opamp compensation. Okay, so I've drawn it out in a kind of 3 dimensions here again. So we've got some frequency omega, and it's got an imaginary and a real part, and that's our feedback network H of S, and we've got our omega and our imaginary and real, and that's our G of S, which is the transfer function of the op-amp. So this could be drawn out in terms of our magnitude and our phase. Okay, so these are our magnitude plots and these are our phase plots. Now if it turns out that the phase plot at a particular frequency is maybe minus 70, and at this same frequency here it's minus 110, so at that particular frequency the phase is going to be a minus 180, so it means that at that frequency the op-amp is not going to work properly. Okay, so we need to make sure that find a way of ensuring that this positive feedback doesn't occur due to this phase shift. Okay, so any noise at that frequency is going to be amplified. Now it will be amplified if the value of our G of omega times H of J omega is greater than 1. Okay, so if it was less than 1, the signal wouldn't get amplified, it would be attenuated. Okay, and if it was attenuated, then it would still be stable, but we wouldn't get the proper signal at that frequency. Okay, and if it was greater than 1, then the signal would get amplified and it would be unstable, and if the signal was actually equal to 1, then we would have something that would oscillate. Okay, we would have the beginnings of an oscillator, but we're not going to be covering oscillator circuits in this. I may do another video series when I get into the RF circuit design. Okay, so there's 2 ways of ensuring that this circuit is stable. What we're going to do is we're going to look at a couple of ways of determining the stability first of all. So the first one is to look at something called the gain margin. Now what we want to do is find the value of the frequency omega naught at which the phase around the loop is a minus 180 degrees. Okay, so then the system, it would be stable if the closed loop gain was less than 1. Okay, because it means that although it's 180 degrees out of phase, at that particular frequency there is no gain in the system, or the gain is less than 1, so it means that the signal would be attenuated as opposed to amplified. Okay, so the margin by which this is less than 1, the gain is less than 1, is called the gain margin. So you can see that here in these couple of bode plots. So we've got one bode plot here where the gain is 100 dBs, it drops off at 20 dBs per decade, and then 40 dBs per decade. So in this instance here, the passband is at this point here, okay, and the frequency axis. Now if we were to look at the phase response, and there's a phase response here, and let's imagine the phase response is a minus 180 degrees at this particular frequency here, then this op-amp would have a problem, because at that frequency there we've now got positive feedback, and that signal would be amplified by 20 dBs. So this would be unstable. Okay, what we say is the gain margin would be minus 20 log to the base 10 of the value h of omega g of omega. That's the magnitude of it, and that's going to give us a value in this case here of 20 dBs, but its gain margin is termed as minus. Okay, so it's a minus 20 dBs, so it would be unstable. Okay, now in this instance here we've got a different op-amp, and we can see here that there's a 180 degrees phase shift at this particular frequency here, but at this frequency here the gain is minus 20 dBs. Okay, so there's actually an attenuation, so it means the signal's getting attenuated. So we can say that the gain margin is minus 20 log to the base 10 of the minus 20, which is equal to 20 dBs. Okay, see that, so it's equal to 20 dBs. So it means that this particular op-amp would be stable because we've got a gain margin of 20 dBs. Okay, so we're saying that we've got 20 dBs of attenuation there at 180 degrees. Okay, so that's the idea of our gain margin. Now another way of looking at this is in terms of a phase margin. Now if we find the frequency where the loop gain is 0 dBs, okay, so there's the loop gain is 0 dBs, and we find the frequency, we've got that frequency, and we will look at, come down and we have a look and see what the phase is at that particular frequency. And if we make sure that the phase at this 0 dBs is got to be less than the 180, so that means that at no point along this curve is there a gain at 180 degrees of phase shift. Okay, so that means that if we ensure that that's the case, and we actually put a margin in, and a margin of a typical margin of say 60 degrees, so in this case we're 60 degrees of a margin here. Okay, then this margin here is called the phase margin. Okay, so that's the two methods that we use in order to have a look at stability and defining control stability. So in conclusion then, we can see that if we were to draw out the network here where we have our gain of the op-amp, the transfer function of the op-amp A, and our feedback transfer function B, we can say gain equals A upon 1 plus AB. So we've seen that derived previously. If the feedback here was a purely resistive feedback, it would mean that there's no phase shift in the feedback loop, so the only phase shift that would develop would be the phase shift of the op-amp, which is out of our control. To maximise the gain margin, the gain at omega naught has to be minimised, okay, but the gain A, okay, and the op-amp gain at omega naught is dependent on the op-amp, so it's out of our control. So we must minimise the gain of the feedback loop, that is the gain at B. Okay, now another thing to note is that the worst system stability is going to occur whenever we've got the maximum value of B as opposed to a minimum value, and so if we've got 100% feedback, then these will be the most unstable circuits. So for example, the voltage follower circuit that we've seen previously would be an unstable circuit. Okay, so that's all for this video. In the next video we're going to go on and we'll look at the op-amp frequency response, and we'll actually look at an example of using dominant pole compensation in order to ensure the stability of an op-amp. Okay, so thank you for listening and goodbye.